Greetings and welcome back to the module 8 titled Factors Affecting Chemical Shift. The objective of the session is to understand the various factors influencing the shielding and deshielding of protons. At the end of the session, the learners will be able to judge the factors influencing the chemical shift. We have already discussed about the chemical shift and the shielding and deshielding mechanism, so let us directly get into the factors affecting chemical shift. There are two important factors which are affecting the chemical shift, namely electronegativity and anisotropy. Let us discuss in detail electronegativity and the chemical shift. If you look upon the tabular column which is presented in this slide, the methyl protons of 4 different chemical compounds are having different chemical shift values. See the methyl iodide, methyl bromide, methyl chloride and methyl fluoride. The methyl protons of methyl iodide appears at 2.2 delta chemical shift value, whereas the methyl protons of methyl fluoride appears at 4.3 delta chemical shift value. This increase in the chemical shift value is due to the electronegativity effects of fluorine. The increasing electronegativity in the halogens means that the S electron density around the proton is progressively reduced from the methyl iodide to the methyl fluoride and increased the frequency. As a consequence of this, deshielding effects leads that are shown in the increased delta values. Similarly, if we look upon another example, the chloroform, dichloromethane and methyl chloride. 3 compounds are there, but the protons' chemical shift values are different due to the presence of 1 or 2 or 3 chlorine atoms in methane. The reason is same. The electronegativity of the chlorine attracts the electron cloud of the proton towards itself, thereby it makes the protons a deshielded one. If you increase the number of chlorine atoms, the electronic cloud around the proton is progressively reduces, thereby the deshielding of protons takes place. Thereby it appears at 7.3 delta chemical shift value. And the next effect is anisotropy effects. We all know that isotropic effects exert their influence uniformly in all spatial directions, whereas anisotropy effects acts non-uniformly. The principle of anisotropy effects in organic molecules are associated with the ways in which the pi electrons react with the applied magnetic field, particularly the pi electrons of carbon-carbon and carbon-oxygen multiple bonds. Let us discuss with few examples. If you consider the aromatic ring currents, example is benzene, the best example. See, this benzene is a planar molecule which is having 6 carbon and 6 hydrogen atoms. So all the 6 hydrogen atoms are placed in these directions, and the double bonds present in the benzene is continuously rotating, thereby the magnetic field is created in perpendicular to the ring current. If we apply the magnetic field created by the circulation of electron is opposing to the magnetic field which we applied, and the ring is completely deshielded, whereas the protons which are in planar are having completely deshielded. Anisotropy effects of aromatic ring current: protons around the ring experience increased field and have high frequency chemical shifts. The zones above and below the ring are shielded in nature, so the opposite effects operates here. Let us go to the next example, double bonds in alkenes. See, the methyl R groups and hydrogen are present at the corner of this molecule, whereas the shielding effects is exerted at the center, thereby the corner groups are completely deshielded. The anisotropic effects of the pi electrons circulation in alkenes: the protons of the alkene groups are deshielded. The zones above and below the plane of the double bond are shielding in nature. And the third example is alkyne triple bonds. Since the alkynes are linear, the circulation of electron in the triple bonds creates the induced magnetic field which opposes the applied magnetic field, and the applied magnetic field is in exactly opposes the induced magnetic field. Therefore, the proton experiences the field less than the magnetic field applied and has low precession frequency, thereby leads to the low delta value. Hence, in this module, we have learnt the two important factors which are influencing the chemical shift. One is electronegativity and anisotropy. In electronegativity, the electronegativity of the atom attached adjacent to the carbon having hydrogen increases, then the chemical shift value also increases, because the electronegative atom attracts the s electronic clouds towards itself, that is the s electron cloud of hydrogen, which is attracted by the electronegative atom. Thereby the proton becomes deshielded and appears at higher delta value. And similarly, the anisotropy, the ring current, double bond and triple bonds electrons used to have a current which creates induced magnetic field. That induced magnetic field opposes the applied magnetic field. Then the chemical shift value changes, which we have seen in our previous three examples. If you have any doubts, you can clarify those doubts by attending an online session in a Google Meet platform. The Google Meet link and timetable will be shared through WhatsApp group. Thank you very much for your active participation.